Hello, everyone. Welcome to our Logs of Technology series. In this occasion, we're going to talk about Java 9 modularity in action with Sander Mack. But before that, let's go through the basics. If you would like to start the conversation with our panelists, there's a way to do that. There's in your Zoom client, you can see at the center of your screen in the bottom a place where you can post your question, and the panelist will get those questions from you and he will interact with you. Without further delay, please join me in welcoming Sander Mack. Sander?
Thank you very much, and welcome everybody to this webinar on Java 9 modularity. I will be sharing my screen and booting up the slides. All right, so my name is Sander Mack and I live in the Netherlands. I work with a company called Luminous Technologies. And at Luminous, we do Java development. We do work for clients, but we also develop our own products. And what we learned while developing products is that when you develop products, you need to think about the long term. So that means not just what is handy to do now, but also think about what do the actions that I take now mean for the future of my software. And we learned that modular development is an important key in our architectures to make our products flexible, to make them maintainable, extensible, and so on. So we use a lot of modular technology in Java, like, for example, OSGI, to create modular systems. And then came along Java 9. As you might have noticed, it contains a module system. So a co-worker of mine, Paul Bakker, and we started investigating this module system quite a while ago. And this ultimately also led to us writing a book about it, as you can see here, Java 9 Modularity, released with O'Reilly. And this is what I want to talk about today, because I do think that the module system in Java will have a large impact in the future. And as we'll see, we'll first have to talk about why modularity matters, because obviously it's there for a reason, this module system. And then after we've seen the reasons that we can encounter to actually apply modular software development, then we're going to look at Java 9 modules and what they mean and how they look. So we have some examples as well. We'll look at some code. And after looking at the modules themselves, we'll also learn that we need a bit of a higher level of abstraction as well. So then we're going to look at services, and services are all about making decoupled modules. We'll see how the services layer in the module system enables us to do that. After we've seen both Java 9 modules and services, we're ready for an even cooler, at least I think it's an even cooler application of modules. This is linking, and linking is enabled by a new tool in the JDK called JLink. And this tool enables us to create custom runtime images containing just the modules that your application needs. We'll talk all about this after we learned about modules. Last, I'm also going to talk a little bit about migration, because we all have existing code bases in Java. So what will it take to take these code bases to Java 9 and to also maybe modularize them? This topic in and of itself is in a whole webinar of itself, so we won't go too deep into migration, but I'll tell you enough to know where to start and where to look. So let's start with the reason for modularity. I already talked a little bit about product development and how we want our products to be maintainable, flexible, extensible. And in essence, what we learned is that modularity as an architectural principle for us is the ultimate agile tool. It allows us to add and mix and remix and reuse functionality quickly. And it also allows us to iterate on the internals of a module, and we'll see why that is possible with modules. So to iterate quickly on internals of modules, we also learned that modularity allows us to express our designs, which we all have, right? We have design documents, we have pretty pictures of our application, but to actually translate these designs into code and to have the compiler and our tools help us in enforcing these module boundaries, even at runtime. So this is what modularity brings us. So one of the most important principles in modularity is actually hiding stuff. And this sounds a bit counterintuitive, right? Because why would you want to hide stuff? And it turns out that if you have a module, they are exemplified by the boxes here. If you have a module, what you actually can do is you can encapsulate code inside of the module. And then if you have encapsulated code, you as a developer of this code can evolve this code without impacting any of the users of the external facing code. So what happens typically with a module is that you have a private internal part of a module, and you have an external part of a module that we call a service contract here. And the service contract is your contract to the outside world. So whatever happens inside of a module stays inside of a module. So you can change your implementation without impacting any consumers. So this is the sort of ultimate holy grail that we're working towards with modularity. And of course, we already sort of could do this in Java using our private, public, protected keywords for classes and for fields on classes. And it actually turns out this works fairly well in the small, if you think about how classes collaborate. But if you think at a bit higher level, if you think about packages and combinations of packages, then there was an issue. Because if you have several packages that make up your module, and you wanted to share some code across these packages inside of your module, these classes or these interfaces need to be public. But if you make something public in Java, it means public for everyone, right? Every other class on the class path will be able to access these classes that you share. And oftentimes, this is not what you want. You want to have several packages that are internal to your module, and you want to have several packages that are explicitly for public consumption. So this is what the module system will offer us. It will give us a way to actually enforce this and to have the compiler and to have the Java runtime help us to make good module boundaries. Now, before we move on to the Java 9 implementation, I want to add that if you have encapsulation, that's only part of the puzzle. There's also a second part of the puzzle if you talk about modularity. If you're going to split up your code base into modules, you'll probably get a lot of them. And this also means that you need to have some way of expressing dependencies between modules, because typically a module needs other modules to work. So this is also an important part of modularity in your architecture, but also in a module system if you're going to use it. And this is a second aspect that the module system also adds. So if you look at Java 9, there was a project called Jigsaw, which was sort of the prototype of the module system that led to the ultimate implementation that is now in Java 9. This Jigsaw project has run for quite a while. It has been years in the making. And this is because it's particularly hard to modularize an existing language, an existing platform. So if we look at some of the goals and motivations of Project Jigsaw, it was first and foremost a very selfish goal of the JDK team. They wanted to modularize the JDK. Because what happened is that the JDK grew into a big monolith, right? We have a rt.jar, the runtime of Java, which is a big jar file containing all runtime library classes, from collections to Corba to whatever is inside of the JDK. And this big monolith became hard to evolve for all the reasons that we talked about earlier. There was no true encapsulation between different functional components, and there was no true encapsulation of code to the outside world. So this became a problem. Therefore, they set out to modularize the JDK. But once they started talking and thinking about a module system, it of course is very, very tempting to also open it up to developers, to us, to also now enable us to create modular applications on top of a modular JDK. So this became a second goal for the module system, and this is what we'll be looking at today and talking about. And ultimately, this will lead to more reliable application composition, because modules, as I said, will be able to express dependencies upon each other, whereas our simple jar files before couldn't do that. And the other point, the other goal was to have strong encapsulation of internal implementation details inside the JDK. What do we mean by that? Well, there are many classes in the JDK that are used to implement the functionality of the JDK, to implement APIs, that could be used by application code and by library code, but actually they shouldn't be used. And this has always been in the documentation of the JDK. So things like sun.misc.star or any of the other internal implementation packages, it's always been clear that you shouldn't use these types, but there was no real way to enforce people to actually not use them. So what happened is that many libraries and even application code started using these internal APIs. And this made it very hard, of course, to evolve the JDK, because even though they were internal APIs, people started using them and they became de facto public APIs, making it much harder to evolve and actually create better solutions with that. Now, a fourth goal of Jigsaw was to actually improve the security of the platform. And this was not a main goal. This is more of a side benefit of encapsulation, and it will have to prove itself still in the wild, whether this actually will be offering improved security. But many Java zero-day exploits actually were based on code in a library, for example, allowing you to reflectively access, for example, the Sun MISC unsafe class, which is a class that allows you to break out of the JVM sandbox. Of course, this is very bad. So if you can actually encapsulate such dangerous internal implementation classes and encapsulate it so strongly that no other code can reach it, no application code can reach it, then you actually have a better story once there is a zero-day exploit in any of the application or userland code. Again, this is something that will have to run its course in actual practice, but it's definitely one of the points that might offer improvement. So if we look at modules in Java, the first thing we have to look at is how the JDK itself has been modularized. So what you see here is a module graph, and this is actually a partial module graph of the modules that are in the JDK. And of course, we're not going to look at all these modules in detail, but you can already see that we have many modules with really distinct names. For example, the desktop module, and we have an XML module, logging module, making it already clear how the functionalities of the JDK are split up and how they relate to each other, how they are depending upon each other. So what you see here is that there are many, many modules in the JDK. In fact, there are even more than 90 platform modules in the JDK 9. And what we see here is the subset of the official specification modules. So the official modules that should be available in every Java implementation. Now, the other thing that you see here is that at the bottom of this picture, there's one java.base module that all modules point to. And this is for a reason. Java.base contains all the foundational types of Java, like Java Lang Object, the Java util package. It contains things that no other piece of code can do without. So every module in Java 9, every module will have an implicit dependency on Java base. You don't even have to explicitly define it yourself. Now, looking at this module graph, you will also find that there are no cycles in this graph. We all know that cyclic dependencies are bad because they make it harder to build and reason about code. Cyclic dependencies are forbidden in the Java module system, meaning that at the module level, you cannot have cyclic dependencies. You can still have inside of a module, of course, classes that have cyclic dependencies or even packages that have cyclic dependencies if you want that. I think you shouldn't, but if you want that, you can still do that. But at the module level, everything has to be acyclic. Now, if we look at applications, then the user view that we have on an application is through the class path. Modules allow us to move beyond the class path. And what we'll see in a demo later as well is that this makes applications more reliable. Because on the class path, you can actually have multiple jar files of the same version of a library, for example, by accident. And this might or might not work at runtime. You will only find out when the application is actually running. Or you might miss a jar file and nothing will complain until the class is loaded that you need from this jar file. And this might happen in some obscure corner case where a user clicks some button in your application, this triggers the class loading, and then it blows up at runtime, which is obviously bad. So in practice, modules move beyond this. By having modules with explicit dependencies, we can actually have a module system that checks for us whether whatever we want to start is complete and whether it results in a valid module graph. So we can say goodbye to the class path. I say can because obviously in Java 9, the class path will also still be there. So using modules in Java 9 is optional. There's no need to actually start using modules once you move from Java 8 to Java 9, but you can. And we'll see that using modules definitely has many advantages, but at the same time, we have lots of existing code bases that we might not directly want to move to a modular world, so you can just keep running those on the Java 9 class path as well. So I talked about explicit dependencies, and what this means is that If a module, for example, my module here, needs to use code that lives in a different module, other module in this picture, then there needs to be a so-called requires relation from my module to the other module. We'll see later how we can express this requires module in source code, but for now, it's enough to understand the concept that we need to have some way of expressing these dependencies. And of course, like I said, these dependencies aren't just there for fun. They're actually used by the module system to verify whether, if you, for example, start my module, that the other module is also available. And if this is not the case, you will get a nice error message rather than some obscure class loading error at runtime. So besides explicit dependencies, we also talked about strong encapsulation, where you want to hide your internal details. And this is also possible using the Java module system. So here we see that my module has a requires relation with the Java base module, which we all knew. Every module has a requires relation with Java base. But we see that this Java base module is actually separated into two parts. The upper part here, containing the Java lang package, the Java time package, and the Java util package, and many more packages that I haven't listed here, these are so-called exported packages. And these form the API of the module. If you are going to use code from Java base in my module, these are the packages that you can use. Now, APIs, of course, also need an implementation. So what you see at the bottom of the Java base module is the com.sun package, for example, the sun.star package, JDK internal. These all contain internal implementation classes. And these internal implementation classes, they actually exist to implement the APIs that you use, but you cannot directly use any code inside of these packages. These are encapsulated inside of the module, inside of the Java base module. And this encapsulation is actually so strong that you cannot even work around these access restrictions using reflection, which is a big change, of course, because we used to be able to do everything using reflection in Java. So these access checks are quite deep at the VM level. And this is something that you will need to be aware of when creating modular applications. Now, some people ask, so why not just use, for example, an existing technology for modular Java like OSGI to modularize JDK and to use that as a module system? And the answer there is both political and technical. So I won't comment on the politics between the OSGI Alliance and Oracle. But if you look at it, OSGI is a solution built on top of the JVM. And it can't really be used in that sense to modularize the JDK itself without large changes. And this wasn't something that was on the table. So you could still say, okay, why not modularize the JDK with its own module system and keep using OSGI for applications? And to which I say, this is a fair point. I mean, you can still keep using OSGI on Java 9 just on the class path and just use it on top of the modular JDK. There's no problem with that. It's just that OSGI itself as a technology has never seen a real mass or big adoption. And this meant that the tooling around OSGI has always been lagging and sort of subpar. So with modules being part of the Java platform and the Java language, I think Java modules actually have a chance of getting better support. And we already see that. So things like Eclipse, IntelliJ, Maven, all other tools that we're familiar with already support modules with Java 9, whereas OSGI support has always been lacking. So enough talking about modules. Let's also have a look at some demo code. So what I'm going to show you is a simple demo application that consists of two modules. One is called EasyText CLI, and the other is called EasyText Analysis. And EasyText is a simple application that we can use to actually analyze text and give back a text complexity metric. And this is just to illustrate to see how modules work. So I'm going to switch to the code. And as we see here in our source directory, we don't have our packages in our code. We actually have two module directories. Now, what makes this into a module? The fact that we have some code in a package and also a so-called module descriptor, which lives in module info.java. Now, the other module, EasyText CLI, also has a module descriptor, and we can have a look at this module descriptor. And there we see that we have some new keyword module followed by the module name, EasyText.CLI. And we can also see that it requires the other module, EasyText Analysis. So apparently this module EasyText CLI, and let's have some look at the code as well. This EasyText CLI module is actually using code from the EasyText analysis module. And we can see that by looking at the code. And the important bit is here that we import a so-called Flash Kincaid analysis class, which lives in the EasyText analysis module, as we can see here. And later on, we use this Flash Kincaid class to actually analyze the sentences that we parse. So how does it work? How do you actually compile and run a modular Java application? So for that, we're going to use a new flag on the Java compiler called module source path. And we're going to point it to our source directory, and it understands the layout of having multiple modules like we have here. Now we need to provide an output directory for the modules, for the compiled modules to go into. And what we can do is we can actually provide all Java files to the compiler. Many people forget this because we use build tools who actually arrange all of this for us. But in this case, we're just going to feed these 4 Java files. So the Flash Kincaid, its descriptor, the main class, and the module info.java to the compiler. And if we do that, we get in the output directory a similar layout, also containing 2 modules. So here we have the EasyText analysis module and the EasyText CLI module. And if I click it open, you will also see that the module descriptor has also been compiled into a class file. So this information about dependencies, is also available at runtime. Now, one point I wanted to make about the module descriptor is that you see many new keywords here. These keywords are actually only keywords in the context of module info.java. So if you have other source files containing variables named module or requires, that's perfectly fine. That will still keep working. So now that we have a compiled set of modules, we can run it. And instead of using the class path, we're going to use the module path to run an application. And we point it to our output directory containing the 2 modules. Then we're going to start the EasyText.CLI module. We also need to point it to the right class because we haven't built a jar around it containing an entry point. So in this case, I'm going to say EasyText.CLI.main, which is the class that we just saw. And if we're going to run this, we actually get our output line, and we can provide a file name, and we get a Flash Kincaid metric. So 83, whether this is complex or not, I'll leave as an exercise to the listener. But we have working code. Question is, what's the difference between the class path and the module path? Well, I already talked about these explicit dependencies. So what would happen, for example, if we remove this EasyText analysis compiled module? So let's move it to trash. And we're going to run the same application again. In the old situation with the class path, it would break somewhere in our application code once we got to the class loading part of loading the Flash Kincaid class. If we start this application now, something else happens. The module system starts resolving all modules that are necessary, and it will tell us that module EasyText analysis was not found, and it's required by EasyText CLI. So here we see that having this metadata available helps us both at compile time and runtime. And I'll also show you that module info can contain export statements, and this controls which of the packages are visible to the outside world, are usable in the outside world. So as you can see here, this module exports the Java Modularity EasyText analysis package. If we remove this export statements, then we have an empty module descriptor. And by default, if you don't export anything, all packages are encapsulated. So if we try to compile the same application again now, using the same Java compiler statement that we had before, then you will see that we get an error. And in this case, it says, okay, this package that you're trying to use from the CLI module is not visible. So it's declared in module EasyText analysis, but it does not export it, which means we cannot compile against it. So this is how you can actually encapsulate internal implementation details if you want to. Of course, in our case, we want to have the export statements, and we want to use this class. But at the same time, this way, you can actually encapsulate code by not exporting it. Now, if we look at this code in Flash Kincaid, we see that it's a public class. So this is actually a pretty big change to the accessibility rules in Java, right? Before, if you had a public class, then you could just use it anywhere. In a modular world, you can only use this public Flash Kincaid class if it's exported from the module. So that's something to keep in mind. So we're now going to switch back to slides again, because there's another concept that I want to talk about. And it has to do with the fact that we have two modules now, which is great. But at the same time, we have a very tight coupling between these two modules, because we actually use this Flash Kincaid implementation class, and we directly instantiate it, and we use it that way. So what happens now if you actually want to have more analysis implementations? What you would like to have is some sort of abstraction, for example, an analyzer interface. And the CLI module would only have to know about the analyzer interface, and then somehow it would have to get instances of this interface without having to know about the specific constructors, like here, my interface, new my import. We don't want to know about that. We don't want to have this tight coupling. The question is, how are you going to use the implementation code if you can't access it? Because ultimately, we would want to hide classes like Flash Kincaid inside of a module. And this is where services come in. So like any problem in computer science, you can just introduce another level of interaction and things will be solved. So that's also what happens here. In a module system, you can also use services in a service registry, which means that you will get provider modules providing services and consumer modules consuming services. But there will be no direct relation anymore between these providers and consumers. There will be a service registry in between. And the provider modules and consumer modules can agree upon an interface as contract between them. So what would this look like in the modular world? Here we see an example that contains an API package. And the idea is that the API package, of course, contains some interface that we want to share between consumers and producers. And now, if we want to consume instances of this API, we need to require my API because we need to know about the interface type. But we also can add a new statement to the module descriptor, which says, okay, this module uses anything that implements COM API my service. So again, here we only use the service interface type. We don't know anything about concrete implementation types yet. On the other hand, we have module myProvider. And the provider module here also needs to require my API because the interface is in my API and we need to implement this interface in the provider. But at the same time, we can also add a provides with statement in the module descriptor. So we say this module myProvider provides an implementation of COM API my service, and it provides it with myProvider.myService import. And the crucial thing here is that myProvider, the package myProvider, isn't exported from module myProvider. So it's encapsulated. And the other crucial thing is that module myConsumer doesn't have a direct relation with myProvider anymore. There's no require statements to myProvider. And the module system will be able to wire up these consumers and providers together based upon the interface type. The only question left is, okay, how does this look in code in myConsumer? How do you actually get instances of my service? And for that, you can use the Service Loader API. And this is an API that has been in Java for a long time already, but it has been reinvigorated for the module system. And you can actually call Service Loader load, provide myService.class as the type that we're interested in, and we get back a Service Loader object. And Service Loader object also implements iterable, so this is very convenient. And if we iterate over this Service Loader object, then we can actually get our service instances and call methods on it and do something with it. So this is sort of a service locator pattern implementation, but it does show the power of decoupling between modules, because myProvider can now encapsulate the implementation, and myConsumer doesn't have to have a requires relation anymore to a specific provider for the service. Now again, let's look at an example, and we're going to look at how we can extend the number of algorithms using this mechanism. So where we don't have to change any codes to add new providers for new algorithms to analyze text. And at the same time, I'm going to show that we can also extend and make the application extensible by creating a new front-end module that uses the same implementation modules, the same analysis modules. And this is a GUI module, a JavaFX GUI, and we'll see how it works in the demo. So I'm going to switch to another demo, which contains the application that we just talked about. And you can see we have multiple modules. The important one is, of course, that we have an API module containing, in this case, the analyzer class that we're interested in. This is just a simple, normal Java interface, nothing special about it. There's a getName method, analyze method. And the idea is that our GUI module, our GUI frontend module, now only has to know about this analyzer interface. So it can do a call service loader.load, give me all analyzers that are there, and then it will actually get back the instances through the service loader. Of course, if we have a consumer module like this, we also need a provider module. So there's a Coleman module and a Kincaid module, providing both a different implementation of text analysis. So let's look at Coleman Analyzer. Again, a plain Java object. There's no anything specific about service loader about this. It implements analyzer, implements the getName method, and also implements, of course, the analyzer method that gives back the value that we're interested in. And as you would expect, this provider module requires the API module because we need to know about the analyzer interface that lives here. But it also provides the analyzer with the Coleman Analyzer implementation type. And again, this Coleman package isn't exported, so it's truly encapsulated, and we can rename it without any problems, without breaking consumers. We can move it to a different package as long as we update our module descriptor, and it won't affect our consumers. So this is something that really shows the benefits of having encapsulated code. Now, if we look at the module info of our front end, then we see, because it uses JavaFX, we also need to require some JavaFX platform modules containing the APIs that we use for our GUI. And again, we require our API. We have a user statement for the analyzer interface type, and this allows the module system to tie together the service providers to this service consumer. There's also a special line here about exporting the Java Modularity EasyText GUI package to JavaFX Graphics. This has to do with the fact that JavaFX uses reflection to instantiate our main class. And as we know, by default, packages are encapsulated, and it's not even accessible to JavaFX in that case. So we need to export it, and in this case, we only export it to the JavaFX Graphics module, so any other module still can't access the GUI package, but JavaFX is allowed to access this package. And now, with that in place, we can start the application. So I have a little script for that I'm going to use. And once this runs, we'll actually see an application here that we've just started. And we can choose between the two algorithms and calculate some value. And in the case of the Flash Kincaid algorithm, we got a different value. And again, this uses services at runtime to wire together this front end to the backend implementation. So if we look at what happens if, for example, we leave out one of the compiled modules. So what I'm going to do is I'm going to remove the Coleman jar, the Coleman modular jar from the module path. And we're not going to recompile. We're not going to change any code. I'm just going to run the application again. Only it now has a service provider less on the module path. We're going to run the application again. And now, hopefully, we'll see that there's only one service implementation available. And of course, this also works the other way around, right? So if we add new implementations to the module path, new provider modules to the module path, then this drop-down will be automatically populated with new analysis implementations. So this is one way to make extensible applications and to decouple modules in a way that's really beneficial to your architecture. So just to illustrate this example a bit more, so we had the application, the two modules. There still was the CLI module, which we didn't look at, but there's now also an EasyText GUI module. And it has a requires relation with the API. It also has a requires relation with the JavaFX graphics and JavaFX controls that we saw. Those come from the JDK itself. And the Kincaid and Coleman implementation or provider modules also had a requires relation with the API. But again, there was no direct relation between the CLI and GUI modules and the Kincaid and Coleman modules. And that's exactly what we want. We don't want to change code or module descriptors or whatever if we add a new implementation of our analysis interface. And we could do this because of the service loader, because of the services mechanism that we had. So at runtime, the service loader brought together the implementations that were in Kincaid and Coleman of the analyzer interface, and it offered them to the consumers, to the consumer modules, the CLI, and the GUI modules. Now, another cool thing that you can do once you have a modular application is to use a new tool called JLink. And linking is actually, you can view it as a new phase of development, of Java development, that's in between compilation and runtime. It's an optional tool, it's an optional phase, but it's actually pretty cool. And what it allows you to do is to create a custom runtime image, which is like a custom JRE. And this JRE only contains the modules that your application needs. That means your application modules will be in there, but it will also find out which which JDK modules your application actually needs, and it will put only those that your application needs into this runtime image. So you can use this for distribution to create a small distribution containing only actually the code that your application needs. And if, for example, you build Docker images based on Java code, this will allow you to make them smaller. It also allows for a whole program optimization pass to happen in JLink because everything comes together there. And there are actually some already implemented in JLink. This is actually something that I believe that will only grow in the future. JLink is pluggable, so there will be the possibility to plug in new optimizations there. But this is still some new territory for the Java world. But again, we can talk long about this, but I'd rather show you how it works. So I'm going to go back to my EasyText example, the last one with services. And I'm going to show you how we can actually create runtime images. I'm going to start the application and compile the application once more so that we have all modules in place. So with that out of the way, we can get back to creating an image. And for that, I'm going to use the JLink tool. And here I invoke JLink with a module path, with a path to our application jars, but I also provide a path to the modules that are in the Java JDK. Why is that? Well, that's because you need to be explicit about which JDK you're building a runtime image for, because these runtime images that we're going to create are platform and architecture specific. So in this case, I'm just building a Mac runtime image on my Mac. But I could also download the Windows JDK and point JLink to, for example, the Windows modules in the Windows JDK. And then I would create a runtime image that is runnable on Windows. So besides the module path, I need to indicate to JLink which module I actually want to have as sort of the root module of this custom runtime image. So this kickstarts the resolution process. In this case, I'm going to create a module based on the CLI module. And what happens is that JLink will take this EasyText CLI module and it will traverse all the requires and all the transitive requires and dependencies of the CLI module. This means that the EasyText analysis module, for example, will be automatically included. What it doesn't do is traverse the provides and users relations between modules. So if I want to have provider modules in my runtime image, I need to add them explicitly, like I do here. So there's add modules, EasyText, algorithm Coleman, Kincaid, some other. And then I can also specify a launcher, which is a launcher script that will be generated into the runtime image with which I can easily start my application by just running the CLI script. And it will then start the EasyText CLI module. Then there are some optimizations that I can apply. And if I build this image, what I get back is an image directory. And it contains a bin, conf, include, legal, lib. So it's like a small JRE, but just tailored to your application. And if I look in the bin directory, then we actually see that it contains the Java runtime, Java command, the key tool command, which is part of Java base. So that's why it ends up here. But also we see that there's a CLI executable. And if we run that, we actually get our application directly running without fiddling with the module path or anything. It's all set up for us. Now, the cool thing about this is that the size, and let's go back, the size of this image is actually fairly small. It's 21 megabytes. So if we compare this to, for example, my Java home directory containing a JDK. So if we do it like this, then you'll see that at more than 400 megabytes. This is much, much, much larger than the custom runtime image that I just created. Why is this? Well, that's because in the image, if we're actually going to ask the runtime that's inside of the image which modules are in there, you'll see that my application modules are in there. So the API, Coleman, Kincaid, CLI, syllable counter. And from the platform, only the Java base module is included because our CLI is a simple application. It only uses the Java base module. Now, on the other hand, if we're going to do the same thing for our GUI module, so here I take the GUI module as a root for our custom runtime image, and I'm going to create this image. This will take a bit longer because it's a bigger image. We're going to do the same list modules there. You will see that there are many more platform modules in there now because we use JavaFX modules, and those in turn have dependencies on other JavaFX modules and other Java modules, Java Desktop, etc. And if we're going to look at the size of this image, you'll see that it's actually fairly bigger. It's still not as big as a full-blown JArray, but it's already a bit bigger. So I hope this demo showed you the applications of linking and what you can actually do with it and what you can gain with it. Of course, the prerequisite here is to actually have an application that is modular, that uses modules. So you can't do this for an existing class path-based application. But still, this is one of the advantages that you work towards once you start modularizing application. Now, what can you do to prepare for Java 9? So let me talk quickly about migration as well. So you can actually use a tool called JDApps, which is shipped also with Java 8, to audit your code and find if it uses any of the internal implementation classes that are encapsulated in Java 9. And there are some command line flags, which we won't go into now, like add exports, as shown here, that you can use to migrate code that actually does use this and that cannot be changed yet, for example. So again, if you're interested in migration, I do have some talks about it on YouTube. Also, the book contains 3 chapters that are exclusively about migration. But the thing that I now want to talk about is that it is possible to gradually migrate from a class path-based application to a modular application. And I'll show you what you should do. So let's say we have a demonstrator.jar file, which is our application running on the class path. It has a dependency on commons-lang, which is just a Java application dependency. And of course, it runs on top of the modular JDK, so there will be a link to Java base, but that's handled automatically for us if we run on the class path in Java 9. So what is inside this demonstrator? Well, a simple class that just uses some commons-lang class to do leftpath, because we all know we need an external dependency to do leftpath, right? We learned that from the Node.js guys. So we have this dependency, this code, and if we compile it on the class path, it's fairly simple, right? We just put commons-lang on the class path, we compile our class, and then we run it by also putting our class on the class path, and in addition to commons-lang. So this is just the old situation. Now, what if we wanted to make this demonstrator.jar into a module? Then we would have to create a module descriptor and actually require somehow commons-lang. But commons-lang isn't a module, it's on the class path. And modules cannot reach the class path. This is crucial because if they were allowed to just use the class path, then it would be it wouldn't have the guarantees that we just saw about reliable application composition, encapsulation, etc. So somehow we need to make sure that commons-lang is also usable as a module. But the problem is, it's not our code. So we could try to patch it, which isn't very nice and may work if you have one dependency, but doesn't work if you have typically 30, 40, 50, whatever dependencies. Also, you could wait for maintainers to create the module descriptor for you, but you don't want to. So we have a bit of a problem there. So the solution there is automatic modules. And with an automatic module, you can actually take a plain jar file, so a jar file without a module descriptor, which lives on the class path, and put it on the module path. And then it becomes an automatic module. And the name of an automatic module will be derived either from the jar file name, which isn't very good, of course, but sometimes it's the best we can do. Or if it's present, there can also be an automatic module name header in the manifest file, which is of course better because then the library already picked a name for you. And of course, because there's no module descriptor, we have to assume some defaults. So the default that is assumed is that every package is exported. So that doesn't make it a very good module, but at least it's usable. And also an automatic module will automatically read all other modules that are currently resolved, because otherwise, well, we don't know what the actual dependencies are because it's just a jar file without a module descriptor. So again, this is the best that we can do. But if we do that, we actually now have the possibility to add a require statement for Commons Lang into our module descriptor, which is what we wanted. And now we can compile this on the module path, module source path, by putting our lib directory on the module path containing Commons Lang. And we can run the same application by putting our own module, our demonstrator module, on the module path alongside the lib directory containing the Commons Lang jar. So with this, we actually took our own code and we modularized our own code by creating a module descriptor without having to wait on the dependency Commons Lang to become a real module. So while this is, of course, a transitional feature, I think it's a very important feature because it allows us to actually migrate our own code without having to wait on all our dependencies. So to wrap it up, I've shown you a lot about the Java 9 module system, and you've seen why we think it's a good idea to actually modularize your code and how you can do that using Java 9. What I think is also very good to stress here is that it's now part of the language. It's in the spec, it's in the VM, it's in the compiler, it's everywhere. It's also supported by a lot more tooling than other module systems in Java. So, like I said, IntelliJ, Eclipse, all the big tools and all the big vendors actually support modules now. So that's good, and it will give us modularity throughout all development phases. In that sense, I believe that having the spotlight on modularity is actually a good thing. Even though we might not get to use it in all our applications or right away, I think it's really, really good to think about how you can apply this in your upcoming developments and how you can start with a modular and solid base from the start. So with that, of course, I would like you to check out javamodularity.com, which contains information about the book that we've written about the module system. Like I said, it also contains lots of information about how to take applications from a non-modular world to the Java 9 module system. And besides that, there's, of course, much more in Java 9 than just a module system. So if you're interested in that, I do also have some Pluralsight courses that you may want to check out at this URL. And I also have some free months of Pluralsight to give away. So if you would like a code, please follow me on Twitter at this handle. Just ping me and I'll provide you with a code for a month free Pluralsight. So with that, this is the end of my talk. And I think it's time to switch to some questions and see if we can answer those. So let me see if I can actually get to the question panel. Okay, so I see that there are two questions currently. I'll start with the top one. The question by Sergey is there any versioning of modules similar to OSGI? And it's a very good question because it's something that's often closely related to module systems, right? And the answer here is I believe, realistic, but also a bit disappointing. Meaning, no, at this moment, there's no notion of versioning in the module system. There used to be in earlier prototypes, but it turns out that many of the frameworks and tools that do use versioning for dependencies, like, for example, Maven or Gradle or OSGI, like mentioned here, they don't really agree on version syntax. They don't really agree on what it means to do version ranges. They don't really agree what it means to do version selection in terms of when conflicts arise, when to choose which. So it was very hard for the JDK team to actually select one of those approaches and bless this approach and actually put it into the VM spec, to the language spec, etc. So instead, the approach that they chose is to be pragmatic and to push out the module system as is. So what you currently should do is that you use tools like Maven or Gradle to actually download and define dependency versions and download those versions onto the module path. And then at compile time or at runtime, the JVM or the compiler will pick up this module path and then do its sanity checking based upon the modules that have been downloaded. So if you have any duplicate versions in there, it will be detected. It will be given as an error, but you won't be able to have the module system select the right versions for you or something like that, or even run multiple versions concurrently. So I say this isn't possible. That's not completely true. It is actually possible if you use some more advanced APIs. There's in the APIs, there's also a concept called layers or module layers. And if you use the module system like I've shown, you just get one layer, which is the boot layer. But you can actually create your own layers. And within different layers, you can have different versions of the same module, actually. And the book also contains some great examples of this. But this is not something that you would easily get out of the box. So you have to do some work for that, and you have to write some code for that to work. So I hope this answers the question about OSGI. I've also seen a question about module.info.java. The question is, will they become very large files in the future? No, I don't think so. At least I hope not. Because if you have a module that's so big that you need to list many exports, or that has so many dependencies that you have a very, very large module info, module descriptor, then I would argue that it's not a very good module, right? It's probably not doing something, not doing one thing and doing it well, the Unix philosophy, but it's probably doing a lots of things and using lots of other modules and probably not doing a great job of it. So if you get a very big module info to Java, that should be a red flag for yourself, and it should get you thinking, okay, how can I further decompose this module into smaller modules that hopefully don't have that many dependencies or that many packages to export. All right. Then there's a third question about when Java 9 will be mature enough to be a platform for production. That is a very good question. And the answer to that is Oracle has decided to move to a quicker release schedule for Java. So we got Java 9 in September. We will already get Java 10 in March, which is this month, actually. And we will get Java 11 in September of this year, and so on and so forth. So every year we will get 2 releases. So what's going on there? Will we have to move to each release, etc.? Well, Oracle also said every 3 years we will also point out a long-term support version. And the first long-term support version after Java 8 will be Java 11. So that's the version that's arriving in September of this year. I believe this is the point that most people will encounter the module system, because Java 9 has the module system, and it will be the same in 10 and 11, etc. It will just be there. It's just that I believe that most people will be switching to a new version of Java when Java 11 is out, simply because it will be the first long-term support version of Java that Oracle has pointed out. Then there is a question if it makes sense to learn Java if Java modularity works like Spring. So what Spring does dependency injection between different parts of your application. And this is sort of similar to what we saw in the services example, only there we had to look up our services. But still, Spring is also all about decoupling components in your application. It's even the case that you can use Spring together with the module system to make it even better. And there's a chapter in the book about that, how we take an existing Spring application and use Java modules to actually enforce boundaries and to modularize it. So I don't think it's either using Java modules or using Spring. It's about, if you're using Spring, do you also want to use the Java module system to help you enforce boundaries at compile time, for example? And if the answer is yes, then it definitely makes sense to learn about it. So there's a new question coming in. It looks like Java 9 modules are based on a package name. What if 2 different dependency jars contain the same package? So indeed, the exports are based on packages. and the requires that we saw are based on module names. So if you have two modules exporting the same package, and this will be flagged as an error by the module system. So this won't be possible, simply because if you have two modules offering the same package, and then it wouldn't be able to distinguish between those when linking and wiring them together. So that's just disallowed. Then there's another question. How much is Java 9 backward compatible? Can I just switch my Spring Boot and Maven project to Java 9 and hope that everything works? Again, that's a great question, and that's a whole other talk in and of itself. The short answer is, if you upgrade to the latest versions of your tools, so the latest version of Maven, latest version of Spring Boot, then you have a very good chance that everything will just work. There are some caveats though, and that has everything to do with the fact that Java 9 encapsulates APIs. So if you have dependencies that do use encapsulated APIs, you may run into some issues. Also, if you have applications that depend on some of the enterprise APIs that are shipped with Java SE, like JAX-B or Corba, or these are all deprecated for removal and are not resolved by default. So this will give some issues. What I would recommend is search on YouTube for my name and Java 9 migration, and you'll find a talk that addresses all of these issues in more depth. So there's a question by Boris: what if you need to export more than one implementation of the interface? This is perfectly possible. So you can have multiple provides with statements in your module descriptor, just like you can have multiple modules exposing the same interface type as well. So this is perfectly possible, and also this is what services are meant for, right? You can have alternative implementations. Of course, you somehow need to be able to distinguish between implementations if you want to choose one or the other. So that means you need to design your interface correctly so that you can actually interrogate the interface somehow to get the right implementation. But that's up to you to design that. So let's see, many more questions coming in. Is every Java 9 module loaded by its own class loader, like in OCI? No. The class loading setup is the same like before. So we have the system class loader, there's a boot class loader, and there's an application class loader, and your modules will be loaded in the application class loader. This is an explicit choice because they wanted to stay backward compatibility in terms of class loading setup. So this is different than in OSGI. Does it make sense to use Java 9 for a project now? I would argue there are two different scenarios here. On the one hand, there's the question of should you use the Java 9 as a deployment, as a runtime platform now? And I would say I would be cautious with that. And like I said, I believe Java 11 will be the first big moment where people actually make this move. But it does make full sense to actually try and run and compile your code in your development stack using Java 9, because it will help you find lots of problems that will also be present if you move to Java 10 or to 11 or to 12 or whatever. So in your development stack, it makes sense, at least to me, to keep track of the latest releases of Java. So test against it, compile against it, see what happens. And then if you want to be more conservative in your production, which I would understand, then just keep running Java 8 there for now. So there are many questions coming in now. I'll just pick a few. I'll pick two more. There's a last one. What about microservices architecture with such a modular approach? Will it be easier to develop? Yes, I believe the same principles apply if you develop a microservice internally. If you build it in a modular way, you get the same benefits. It's even the case that you might not want to start out with microservices, but that you might want to start out with a modular application. And in this modular application, you have well-defined module boundaries, just like you would have in your microservices architecture. You would have well-defined interfaces between modules, which you also would have in your microservices architecture. But you don't have the downsides of having a network boundary in between and having all the complexity of a distributed system. And then when time comes that you do actually need to scale out some part of your application, then it will be possible to just pick out the set of modules that implement this part and then put those into their own microservice and deploy them independently, etc. But you've already done the hard work of actually decomposing your application into modular, into functional decomposed parts. So again, this is something that I've thought about a lot as well. And if you want to have some more information about that, search for a talk by me called Modules or Microservices, and you'll get a full hour of content on this very topic. So let me pick a last question. And there's the question, is it possible to add new modules providers to a project that is already built by J-Link? Yes and no. So it's not possible to add these provider modules to the J-Link image itself after the fact. So you would have to build a new one containing new providers. But it is still possible to also run the Java command that's inside of J-Link with a custom module path. So you can still add modules to the module path if you use this Java runtime that's in the J-Link image. So that way you can still put new provider modules on the module path and they will be picked up as well. So with that, I think we've reached our time. And again, if you're interested in more, I definitely think some of the questions point to other talks that I've done, so try and find those. Also, if you're interested in a free month of Pluralsight, follow me on Twitter and ping me, and I'll provide you with a code. And with that, I would like to thank you all for the time and attention.
Yes, Sanders, thank you so much. It was a really useful and exciting speech, exciting presentation. Guys, I would like to ask you to stay online for 1 minute more and fill out a small survey for us to make our LTS series more interesting and useful for you. And again, thank you so much for your participation, and see you on next webinars.
Thank you very much.
Yeah, thank you. Bye-bye.